Welcome to a section on hypothesis testing. This brings together the concepts learned in section 10.2 and 10.3. So we will first do hypothesis testing for the population proportion, and then we will perform some hypothesis testing for the population mean. All right, so our steps for hypothesis testing. So now let's put it all together. So here are the step-by-step procedures for conducting hypothesis tests. Okay, so in this 9-step process, we want to extract important information from the problem. So we first want to write down all the values that are given to us, like x, n, p hat, x bar, and s. Okay. Then from there, we'll go into step number 1, which is the claim. So we'll state the claim in English using a complete sentence. So we'll write out in plain English what the researcher is trying to prove or test. So this helps you understand what you're looking for before diving into the math. For example, we would state something like the researcher claims that more than 50% of voters support the new policy. Okay. Step number 2 is the hypothesis. So here is where we state the null and alternative hypotheses with symbols. Okay, so we'll use the parameters p, mu, or sigma depending on what the problem is speaking to. Okay, so we'll have for the null parameter equals some value, and then for the alternative, the parameter inequality, and then some value. So we want to first convert the English claim into a mathematical notation. We just need to remember that the null always has the equal sign and the alternative always has an inequality. Okay. And this is usually the claim we're trying to prove goes into the alternative. Okay. Step 3 is the level of significance. So we determine the alpha level. So this is usually given in the problem. It's typically either 0.01 or 0.05 or 0.1. This is your tolerance for error. So how willing you are to make a type 1 error. Then we have, for step 4, our critical value at Z and T. So the level of significance is used to determine the critical value. The critical value represents the maximum number of standard deviations that the sample statistic can be from the population parameter. It is the value that separates the probable from the improbable. So depending on whether you are working with a proportion or a mean, you will then have 2 different ways of finding your critical value. For a proportion, we would use the inverse norm test. And for the mean, we would use the inverse t. Okay. So the critical value, I want you to think of as the line in the sand. If your test statistic crosses this line, then we would reject the null. Think of it as the boundary between reasonable and too extreme to be chance. All right, step 5 is our picture. So we're going to draw the appropriate graph showing the critical or rejection region or regions. Remember, the critical region or rejection region is going to be the set of all values such that the null hypothesis is rejected. So we'll draw a normal t distribution curve, a normal or t distribution curve, depending on which one we're working with, and shade the rejection regions. And then the visual will help us see where our test statistic needs to fall to reject the null. So there are 3 different types depending on what type of test you are performing. So the left tail test is going to have the rejection region on the left. The right tail test is going to have the rejection region on the right. And then the two-tailed test is going to have rejection regions on both sides. Okay. Step 6 is the test statistic. So we'll calculate and state the appropriate test statistic, whether Z or T, and then label the test statistic on the graph. So a test statistic is a value computed from the sample data that is used to make the decision about whether or not the null is rejected. It represents the number of standard deviations that the sample statistic is from the assumed parameter in the null. Okay, so for a proportion, we will be using the one prop z-test to find our test statistic. And for the mean, we will use our t-test. Okay, so this is the actual value we calculate from our sample data. So it tells you how many standard deviations your sample result is from the null's claim. Okay, so think of a z-score or t-score that measures how unusual is my sample. Okay, so if it is very far from zero, then that's evidence against the null. Okay, so that's your test statistic. All right. And step 7 is our p-value. So we'll use a calculator to help us find the p-value as well. A p-value is the probability of observing a sample statistic as extreme or more extreme than the one observed under the assumption that the null hypothesis is true. It is the probability that a sample will result in a sample mean, such as the one obtained if the null hypothesis is true. Okay, so the smaller the p-value is, the greater the evidence against the null hypothesis. So a small p-value less than alpha implies that the results are unusual and there is a significant difference from the null, so we should reject the null. A large p-value, so more than alpha, implies that the results are not unusual and there is no significant difference from the null, so we should not reject the null. A memory tool is if the p is low, the null must go. If the p is high, the null will fly. So for proportion, we'll use the one prop z-test, and for the mean, we'll use the t-test to help us find our p-values. So the p-value, remember, answers the question, if the null were true, what's the probability of getting a result as extreme as or more extreme than what we actually observed? For example, if the p-value equals 0.03, this means that there's only a 3% chance we'd see results this extreme if the null were true. So that's pretty unlikely. So the null then is probably wrong. Okay. All right. And step 8 is our decision. So we will state the appropriate decision, whether to reject the null or do not reject the null. So for the classical method, we would be looking at the test statistic and comparing it to the critical region or rejection region. So if the test statistic falls into the critical or rejection region, then we reject the null. If the test statistic does not fall into the critical region, then we do not reject the null. So if the sample proportion is too many standard deviations away from the proportion stated in the null hypothesis, we reject the null hypothesis. Now for the p-value approach, if the p-value is less than alpha, then we will reject the null. If the p-value is greater than alpha, then do not reject the null. So when the probability of an observed event is exceptionally small, unlikely, under the assumption that the null hypothesis is true, we say then that the result is statistically significant. When results are found to be statistically significant, we have evidence to reject the null hypothesis. So these are the two approaches you can take. In this lecture, we will be taking both approaches for all of the problems. However, on assessments, you can choose either one. But because we are doing both approaches, that means we should get the same result for both approaches. Okay. So sample evidence, remember, can never prove that the null hypothesis is true. So when we do not reject the null hypothesis, we are saying that the evidence indicates that the null hypothesis could be true. That is, there is not enough evidence to reject our assumption that the null hypothesis is true. So we never accept the null hypothesis. Okay, so we are going to compare our p-value to alpha or compare our test statistic to the critical value and then make our decision based on which one is bigger. Okay. So think of reject the null as guilty, strong evidence to convict. Do not reject the null as not guilty, not enough evidence to convict. But that doesn't mean innocent. Okay. And step number 9 is the conclusion. So we'll write the conclusion addressing the original claim. So always make sense of the conclusion with a statement that uses simple, non-technical wording that addresses the original claim, and use complete sentences. So when our decision is to reject the null, we will state that there is sufficient evidence to conclude or indicate, support, justify that, and then state our claim. And we stated our claim all the way in step number 1. When our decision is do not reject the null, then we would state there is not sufficient evidence to conclude, indicate, support, justify that, and then state the claim. Okay, so we want to put our decision into plain English that directly answers the research question so that someone with no statistical background would be able to understand our conclusion. And good conclusions include there is sufficient evidence to conclude that. There is not sufficient evidence to conclude that. And a restatement of the original claim in plain English. Bad conclusions will say, we accept the null, which we never say. Or they might say, just stating the p-value without the interpretation, or use jargon without explaining what it means. We always want to make sure that we are answering the research claim that was stated in the problem with sufficient evidence or there's not sufficient evidence. All right. I think we're ready for some problems. So our first example. All right. So in December of 2001, 38% of adults with children under the age of 18 reported that their family ate dinner together 7 nights a week. In a recent poll, 403 of 1,122 adults with children under the age of 18 reported that their family ate dinner together 7 nights a week. Is the proportion of families with children under the age of 18 who eat dinner together 7 nights a week decreased? Use the alpha equals 0.05 significance level. So our first step is to state our claim. And our claim here that our researcher is trying to find is, or states that the proportion of families with children under the age of 18 who eat dinner together 7 nights a week has decreased from 0.38. That is the claim that our researcher is stating. So from there, we can state our hypothesis. So our null hypothesis will be P equals 0.38. So the proportion equals that. And we know that it's a proportion because our problem says has the proportion of families. Okay, so we know we're dealing with the parameter P. Our alternative will be P is less than 0.038 because the keyword here is decreased. That is the claim that we're trying to prove. Okay. So from this problem, we can now go into step 3. And we know that we have a level of significance where alpha equals 0.05. And that too was also given to our problem. Note here that because our alternative is less than 0.3, we are a left-tailed test. So our critical region is going to be on the left side. And that takes us to step number 5. So in step 4, we will find our critical value. So our critical value is going to be found using inverse norm. Our area to the left is going to be 0.05 because that is alpha. And that gives us a z-score of negative 1.645. So in drawing our picture, we will have the normal curve with the rejection region shaded on the left side. Okay. Our critical value is going to be at negative 1.645, and our test statistic marked at Z is going to be in either the rejection region or in the do not rejection region, which is what we'll find in our next step. Okay, So once we've drawn our picture, we now can find our test statistic. Because we're using the one prop Z test in our calculators, it will automatically populate your p-value as well, which is why we can perform the classical approach and the p-value approach at the same time, because our calculator provides both values. So in our one prop Z test, we are going to enter in our p naught, which is 0.38. That is the parameter that we are testing against. Our X is going to be 403. Our N is 1,122 because that's the sample size. And we are testing in the alternative whether our proposition is less than P naught. Okay. And then we would go to calculate. Once we go to calculate, we would get a Z-score, or our test statistic, as negative 1.437 and our p-value as 0.0754. Okay, so we have our test statistic and we have our p-value. So we can go back to our picture and we can identify where our test statistic is going to be on our image. And so negative 1.437 is actually less than negative 1.645. So it lands in the do not reject region. Okay. So that means we are not rejecting the null hypothesis. Okay. But we can also use our p-value to determine if we are rejecting the null or not as well. And that takes us to step number 8, which is our decision. So with the classical approach, we use our test statistic, and our test statistic is not in the rejection region. And then for our p-value, we take the p-value that we found using the one prop Z test, and we compare it to alpha, which is 0.05. Our p-value is greater than alpha, so we know then that we do not reject the null. So for our conclusion, we are going to state that there is not sufficient evidence to support the claim that the proportion of families with children under the age of 18 who eat dinner together 7 nights a week has decreased from 0.38. Okay. So in this example, we were testing, did the percentage of families eating together decrease from 38%? And we found that in our sample, 403 of the 1,122, which is approximately like 36%, eat together 7 nights a week. That's a bit lower than the 38%, but is it significantly lower? And our verdict is no, because the p-value is greater than 0.05. So we don't have enough evidence to say it decreased. The difference could just be due to some random sampling variation. So a practical interpretation of this problem is that while our sample showed that about 36% compared to the 38%, so that is roughly a 2% point difference, isn't statistically significant at the 0.05 significance level, we'd need stronger evidence to conclude that family dinners really decreased. So a lower percentage or a higher sample to help us with that. Okay, let's go to the next one. In 2000, 58% of females aged 15 or older lived alone. According to the U.S. Census Bureau, a sociologist tests whether this percentage is different today by obtaining a random sample of 500 females aged 15 and older and finds that 253 are living alone. Is there sufficient evidence at the alpha equals 0.01 level of significance to conclude the proportion has changed since 2000? 0.1, not 0.01. Okay. So our claim is that the proportion of females who live alone has changed from 0.58. Okay, that's the claim that the researcher is making. So our hypothesis is going to be P equals 0.58 for our null. And for the alternative, P does not equal 0.58 because our keyword here is has it changed? So has it increased or decreased, but it's not specific on which one. All right, so we know then that this is going to be a two-tailed test. Our level of significance is going to be 0.1. Okay. So since we have a two-tailed test for our critical value, we know alpha represents the total area of our rejection region. So to find the area of one rejection region, we're going to have to take alpha and divide by 2, which gets us 0.05. So we'll use this area and enter it into our inverse norm. Okay, and that will give us a z-score of 1.645. Since we are a two-tailed test, we also have a negative 1.645 as well. So for step 5, we now have an image of our normal curve with the rejection regions shaded on both sides. And then our critical values here are negative 1.645 and 1.645. Okay, and then the test statistic will then be marked on this image to determine are we in the rejection region or the do not reject region. Okay, so let's go into step number 6, where we will perform our one prop z test, which will give us our test statistic as well as our p-value for our data. So in our one prop z test, we will enter in 0.58 for our p naught. X is 253. N is 500. And then we are testing whether p naught equals our proportion. And then we'll then select calculate. From there, we will get our test statistic, which is negative 3.3523, and our p-value 0.0075. Okay, so if we pull up our image in step 5, we'd see here that our number is actually larger than our critical value. So it lands in the rejection region. Okay. So now what is our decision? So using the classical approach where we compare our critical value and test statistic, we find that the test statistic is in the rejection region. Then using the p-value approach, we compare our p-value from our data to alpha. And alpha here is 0.1, not 0.01. This should be 0.1. And we find out that our p-value is less than alpha. So both of our approaches state that we need to reject the null hypothesis. So our conclusion is going to be that there is sufficient evidence to conclude that the percentage of females aged 15 years of age and older who live alone has changed since 2000. Okay, so what were we testing in this problem? We were testing, has the percentage of women living alone changed from 58% in 2000? Okay, and what we found that in our sample of 253 out of 500 females, which is a little more than 50%, live alone. Okay, so that is roughly around 6 percentage points lower than the 58%. Okay, but remember, this is a two-tailed test, so we're looking for any change, not a specific amount. So our verdict was that yes, this is statistically significant because our p-value of 0.0075 is less than 0.1. So we have strong evidence that the proportion has changed. So our test tells us it's changed, but it doesn't tell us if it's increased or decreased. Okay, so we would have to look at the data, and it appears to have decreased slightly. So is a 6 percentage point difference practically significant? Well, that's debatable. So while it's statistically significant, it may not represent a major social shift. All right, so we've attempted 2 problems with the population proportion. I would like for you to pause and attempt the practice. All right, welcome back. So you had a practice problem dealing with the American Animal Hospital Association survey that stated that 37% of respondents stated that they talked to their pets on the telephone. A veterinarian found this result hard to believe, so he randomly selected 150 pet owners and discovered that 54 of them spoke to their pets on the phone. Does the veterinarian have the right to be skeptical? Use a 0.05 level of significance. And to be honest, when I travel and I leave my doggie at home, I definitely talk to her on FaceTime. Now, does she understand anything that I'm saying? I think so, but my husband doesn't. But I'll still be talking to her. So I'm definitely a part of that group. So in this problem, we have our step 1, which is the claim. The proportion of pet owners who talk to their pets on the telephone has changed from 0.37. Okay, so we want to know if the pet proportion has either increased or decreased. Okay, doesn't say specifically which one. So we know that we are going to have a hypothesis test where our null is going to be p equals 0.37 and our alternative is p does not equal 0.37. Okay, so that means we're dealing with a two-tailed test. Step 3, level of significance, alpha equals 0.05, and that was given to us in the problem. So to find our critical value, you should have taken your alpha and divided it by 2, giving you an area of 0.025, which you would take and enter into inverse norm to get your critical values. And because it's a two-tailed test, we have a negative and a positive, and those values are 1.96 and negative 1.96. So in step 5, we would draw our normal curve with our rejection region shaded on both tails with our critical values at negative 1.96 and a positive 1.96. Then you performed your one prop z-test where you found your test statistic and your p-value. Okay, so for your test statistic, you would have gotten negative 0.254, and for your p-value, 0.7997. So you would then take your p-value and compare it to alpha, and your test statistic, you would identify it on the image you created for step number 5. You would see that it would land in the do not reject region. So now that you have this information, you can now make your decision. So the classical approach, which compares the test statistic and critical value, you identified that the test statistic is not in the rejection region. And then for the p-value, you compared it to alpha, and you found that your p-value is greater than alpha. Both of them, both approaches, resulting in a do not reject the null. So for your conclusion, you then stated that there is not sufficient evidence to conclude that the proportion of pet owners that talk to their pets on the phone is different from 37%. Okay, so let's understand this example just a little bit more. So what were we testing? We were testing the veterinarian is skeptical that 37% of pet owners talk to their pets on the phone. What did we find? In the vet sample of 54 out of 150, which is roughly 36%, talk to their pets on the phone. So that's very close to the claimed 37%. Okay. And what was our verdict? Well, the vet does not have the right to be skeptical. The difference between 37 and a 36% is so small that it's clearly just random variation. The p-value of 0.7997 is huge, meaning there's about an 80% chance of seeing this kind of difference just by chance. So an interpretation of this is that the vet sample actually supports the original claim, because a 1% point difference with a sample of 150 is truly nothing to worry about. All right. So we just dealt with some proportion problems. So now let's look at some population mean problems. Alrighty, so our first one here. Okay. Note that these hypothesis tests that we're now going to be doing are going to be using the t distribution. Okay. All right. So students who learn English and another language simultaneously score worse on the SAT critical reading exam than the general population of test takers. The mean score among all test takers on the SAT critical reading exam is 501. A random sample of 100 test takers who learned English and another language simultaneously had a mean of SAT critical reading score of 485 with a standard deviation of 116. Do these results suggest that students who learn English as well as another language simultaneously score worse on the SAT critical reading exam? Test the hypothesis at alpha equals 0.1 level of significance and write a conclusion based on your results. So our claim for this problem is going to be the mean score on the SAT critical reading exam from students who learn English in another language is less than 501. Okay. So our hypothesis tests are going to be that the null mu is equal to 501, and our alternative is going to be that mu is less than 501 because we want to test if it is worse. So if it's less than 501, which means that we are a left tail test. And then in step 3, our level of significance is 0.1, which was given to us in the problem. Okay. So our next step is to find our critical value because we want to know that boundary for our rejection and not rejection region. So we will use the inverse t to find our critical value. Okay, so our area to the left is going to be 0.9. Okay, because alpha is always the area to the right. So in our calculator, if you're not able to select left, center, and right, you need to enter in the area to the left, which is 0.9. Our degrees of freedom is going to be 1 less than our sample, and our sample was 100. So our DF is going to be 99. So when we plug that in our calculator, we then get a critical value of negative 1.29. Okay, so for our step number 5, we will create the t distribution curve with the rejection region on the left. And then our critical value is the boundary at negative 1.29 that separates the reject region from the do not reject region. So now we can go into step number 6 and 7, similar to the one prop Z test, where it gives you the test statistic and the p-value. Our t-test here does the same thing. Okay, so we are going to go to t-test and we are going to select stats because our problem gave us the stats. If they gave us a table full of data, then we would need to enter that into our calculator and then we would select data. But because we have stats, we're just going to use the stats that were given to us. So we know mu is going to be 501. That's mu naught. Our X bar is going to be 485. That was given to us in the problem, the mean of the SAT critical reading score. All right. Our standard deviation is going to be 116. That's what the S is. Our sample is 100. Okay, and we're testing whether mu is less than mu naught. Okay, so then we would press calculate, and we'd get a test statistic of negative 1.379 and a p-value of 0.0855. So we'd pull up our image to compare our test statistic t to our critical value, and we see that our test statistic lands in the reject region. Okay, so for our decision, the classical approach, since our test statistic landed in our reject region, we are rejecting the null. And we can then use our p-value approach to justify as well. 0.0855 is less than 0.1, so we also, in using this approach, will reject the null. So our conclusion is that there is sufficient evidence to conclude that students who learn English in another language simultaneously score worse on the SAT critical reading exam. So in this problem, what were we testing? Let's walk through it just to make sure we understand it. Do bilingual students, so students who learn both languages simultaneously, score lower on SAT critical reading than the general average of 501? And we found that our sample of 100 bilingual students had a mean of 485, which is 16 points lower than 501. So in our testing, the verdict was yes, at the alpha equals 0.1 level, this is statistically significant. The p-value of 0.0855 is less than 0.1, so we have evidence that bilingual students score lower. Okay. Some important considerations to think of in this problem are: one, the practical significance. So a 16-point difference on the SAT is meaningful, and it could affect college admissions. Two, the standard deviation. So the standard deviation of 116 is very large. Okay, it's showing lots of variability in scores. All right, it's a big stretch. All right, and then the interpretation is number 3 to keep in mind for this problem. Okay, so this doesn't mean learning 2 languages is bad. It might just mean that these students haven't had as much exposure to reading English literature, which is what the SAT critical reading test emphasizes. Okay. All right, next example. Para-nonphenols is in a polyvinyl chloride used in the food processing and packaging industries. Researchers wanted to determine the effect this substance had on the organ weight of first-generation mice when both parents were exposed to 50 micrograms per liter of this substance in drinking water for 4 weeks. After 4 weeks, the mice were bred. After 100 days, the offspring of the exposed parents were sacrificed and the kidney weights were determined. The mean kidney weight of the 12 offsprings were found to be 396 milligrams, with a standard deviation of 45.4 milligrams. Is there sufficient evidence to conclude that the kidney weight of the offspring whose parents were exposed to 50 micrograms per liter of this substance in drinking water for 4 weeks is greater than 355.7 milligrams, the mean weight of kidneys in normal 100-day-old mice at the alpha equals 0.05 level of significance? Okay. So our claim is the mean kidney weight of mice whose parents were exposed to 50 micrograms per liter of para-nonphenol in drinking water is greater than 355.7 milligrams. Our hypothesis is going to be null, mu equals 355.7, and the alternative, mu is greater than 355.7. So this is a right-tailed test. Okay. Our level of significance is 0.05. That was given to us in our problem. Our critical value. Okay, so since our alpha is 0.05, that's the area on the right. The area on the left will be 0.95. And then our degrees of freedom is going to be 1 less than our sample, which is 12. So 12 minus 1 is 11. That gives us a critical value of 1.796. So for step 5, we can draw our t-distribution curve with the rejection region shaded on the right, with our critical value boundary of 1.796. Now that we have this, we can use the t-test to determine our test statistic and our p-value. So in the test statistic, we will select stats in our calculator. Mu naught is going to be 355.7. X bar, which is the mean, is 396.9. That was given to us in the problem. Our standard deviation is 45.4, and our sample is 12. And we're testing whether mu is greater than mu naught. So once you click calculate, you should get a test statistic of 3.144 and a p-value of 0.0047. So going back to our image in step 5, we would see that our test statistic falls into the reject region. So our decision using the classical approach, we would compare the test statistic to the critical value, and we found that the test statistic is in the rejection region. For the p-value approach, we would compare the p-value to our level of significance, alpha, and we found that our p-value is less than alpha, so we too would reject the null. So our conclusion is that there is sufficient evidence to conclude that the mean kidney weight of mice whose parents were exposed to 50 micrograms per liter of this para-nonphenol in drinking water for 4 weeks is greater than 355.7 milligrams. So in this problem, what were we testing? Does the exposure to para-nonphenol cause offspring to have heavier kidneys than normal? What we found, the 12 offspring had a mean kidney weight of 396.9 milligrams. That's roughly, let me subtract that real quick, 41.2 milligrams heavier than normal. And our verdict was that yes, this is highly statistically significant. The p-value of 0.0047 is very small, giving us strong evidence that the chemical exposure increased kidney weight in the offspring. Important things to consider, I have 3 of them. 1, the small sample size. N here is 12, but the effect is large enough that we still detected it. 2, practical significance. A 41.2 milligram increase is substantial and suggests that the chemical has a real biological effect. And 3, the scientific implication. This suggests that this chemical may have health effects that transfer across generations, which is an important finding for the public health. Okay. All right, now it's your turn. Pause the video and attempt this practice problem. All right, so let's walk through it. So according to the American Time Use Survey, the typical American spends 154.8 minutes, roughly 2.58 hours per day watching television. A survey of 50 internet users results in a mean time watching television per day of 128.7 minutes with a standard deviation of 46.5 minutes. Conduct the appropriate test to determine if internet users spend less time watching television at the alpha equals 0.05 level of significance. So your claim should be that the mean time spent by internet users watching television is less than 154.8 minutes per day, which gives you your 2 hypotheses. H naught, your null, is mu equals 154.8, whereas your alternative is that mu is less than 154.8, which makes this a left-tailed test, and your level of significance is alpha equals 0.05. Okay. From there, you found your critical value. So since alpha is 0.05, which is the area to the right, you need to find the area to the left. So that area would be 0.95. Your sample is 50, survey of 50 internet users. So your degrees of freedom will be 49. That gives you a critical value of negative 1.677. From there, you drew your picture. So you have a t-distribution curve with the rejection region shaded on the left with your critical value that you found in step 4 of negative 1.677 as your boundary. So now you know where your reject region is and your do not reject region is. Your next step, 6 and 7, is to find your test statistic and p-value. Your calculator populates both results for you. So you would open the t-test, identify your stats, enter them into the calculator, and press calculate, giving you a test statistic of negative 3.967 and a p-value of 0.0001. Okay. So now we can identify our test statistic on our image that we drew in step number 5, and we see that it lands in the reject region. Okay, so from there you made your decision in step number 8. For the classical approach, you stated that the test statistic is in the rejection region, and for the p-value, you were able to identify that your p-value of 0.0001 is less than 0.05, both approaches stating that we are to reject the null. So your conclusion: there is sufficient evidence to conclude that internet users spend less time each day watching television than a typical American. So what were you testing in this problem? Do internet users watch less TV than the typical American? What did you find? Internet users in our sample watch an average of 128.7 minutes per day. That's roughly 26.1 minutes less per day. And the verdict? This is highly statistically significant. The p-value of 0.0001 is extremely small, giving us a very strong evidence that internet users watch less TV. So here's our practical interpretation of this problem. Number 1, the meaningful difference. 26.1 minutes per day equals 3 hours per week, which equals over 6 days per year of saved TV time. 2, this makes intuitive sense. So if you're spending time on the internet, you have less time for TV. That obviously makes sense. And 3, the social implications. This was from a 2002 study examining how internet use affects other activities, which is an important question as the internet has become more mainstream today. Okay. All right. Okay, so that concludes hypothesis testing for section 10.2 and 10.3.